Nowadays, making light is as easy as flipping a switch. We now take the convenience of electric light for granted and rarely bother to appreciate it. However, getting to this point was a long and difficult process. Human beings first made light with fire. However, why do flames emit light? As many of you know, flames contain fine carbon particles. The flame heats the carbon particles, causing them to glow and emit light. The question that naturally follows is, why do materials emit light when heated? Materials become unstable when they are heated. The accumulated heat energy dissipates not only in the form of heat, but also in the form of visible light, and the latter becomes the dominant form of energy emission as the temperature increases. This is called black body radiation, a principle that served as a means of making light from heat long before recorded history. In this way, we can make brighter light if we heat something to higher temperatures. When we heat an iron piece to 1000 degrees Celsius with a gas burner, it looks like this. It can be heated to an even higher temperature of 2500 degrees using an oxyhydrogen torch. This makes the iron piece glow even brighter. Like this. But it also melts. Lime was found to be a suitable alternative due to its ability to withstand the oxyhydrogen torch while producing brighter emissions. Let's observe it. It's hard to look at it directly. You may be familiar with the title of a Charlie Chaplin movie, Limelight. This refers to an early-stage lighting apparatus used all over the world before the invention of light bulbs. In the incandescent lamps which succeeded these early chemical lights, an electric current heats a fine metal wire, causing it to emit light. This is also black body radiation. Now we can produce a higher temperature easily with an arc discharge, an apparatus commonly used in metal welding. This lightning-like discharge occurs between two carbon electrodes as blackbody radiation from the heated carbon. The first street lamps in Japan using this type of light amazed people when they were first introduced in 1882. You may have seen mercury arc lamps in gymnasiums, which use a similar principle. Later, a new type of light appeared called cold light. This includes neon lights and fluorescent lights, which generate light without the application of heat. Instead of heat, these lights work by exciting atoms using another external energy source. A fluorescent light tube contains a high-speed electron beam traveling between the two electrodes at the ends. When this beam collides with atoms enclosed in the tube, they absorb energy from it and enter an excited state. The excited atoms release the energy in the form of light. Since nothing is heated in this process, the temperature does not rise. That's why it's called cold light or luminescence. LEDs use a more sophisticated version of this phenomenon. Unlike fluorescent lights, electrons in LEDs collide with densely packed atoms. Thus, the atoms are efficiently excited, providing energy-saving illumination. Do you like it? What a long history of continuous improvements we've had in reaching the convenient artificial illumination we enjoy today.